Hello and welcome. So today we're going to be going through a paper 2, a paper 4 and a paper 6, all from the Cambridge IGCSE Coordinated Syllabus. And yeah, if you're new to the channel, then I am the Argon tutor, a fully fledged chemistry teacher with over 10 years experience. So hopefully I'll be able to offer you some tips and tricks as we go through these papers to get you ready for your upcoming exams. If you haven't done so already, you can download your own copy of these PDFs in the video description. Okay, so let's get started. So we're only doing the chemistry questions. So that starts us with question 14. So we've got a mixture containing solid P and liquid Q. And what do we need to do? So which process to obtain a pure sample of liquid Q? So that's the key thing. You really want to be reading these questions. So we want a pure sample of liquid Q. So we don't care about the solid. So we need to be separating out a solid from a liquid, but we're keeping the liquid. So let's have a look at the feasibility of each answer. So crystallization, is that going to help us? I don't think so. Distillation probably is. Let's just check the others. Evaporation, no, because we're going to lose the liquid then. And yeah, paper chromatography, yeah, this is not used. Paper chromatography is used to separate out inks or dyes or amino acids. So we have our answer. So the answer has to be, distillation. Okay, so on to question 15. We've got three different processes. So yeah, three different processes are listed. We have heating ice to form water, lighting a match, and removing zinc from a zinc chloride solution by filtration. And well, I've got a question here. So what are physical changes? So before we even look at the answers, because yeah, it's always going to be like a combination of all of them, let's just have a think about what is a physical process. So yeah, so a physical change is where we're getting no new chemicals being formed. So we have, so heating ice to form water, that is a physical change. Lighting a match while we're making something new, so it's not going to be that. And removing zinc from a sodium chloride solution by filtration. Well, again, yeah, this is going to be a physical change because we've not made anything new. This is also a physical change. So we now can have a look at what we've got. So we've got this one, so it's 1 and 3. So yeah, so our answer 1 and 3 only. There we go. Okay, on to number 16. So sodium phosphate, and we've got the formula there. Contains some sodium ions, and then we've got aluminium sulfate, contains some sulfate ions. Happy days. But what is the formula of aluminium phosphate? Aluminium phosphate. Okay, so from this, they haven't given us the charge of either aluminium or phosphate, but we can use the charges of the other things that they have given us the charge of to figure that out. So we've got the sodium charge, we've got the sulfate charge, and then from that we can figure out the charge of our missing pieces. So we want this phosphate and aluminium. So looking at the phosphate first, so aluminium is +1, we've got 3 of those, so this has to be negative by 3 to cancel out the plus, plus, plus. Sulfate is a little bit trickier, but also aluminium is also in group 3, so if we can remember aluminium is in group 3, so aluminium, yeah, has to be +3. And this also checks out because we've got, yeah, +3, +3, -2, -2, -2. So they cancel out. So now on to making our formula. So we've got Al3, PO4. So now we have got our 2 valencies here. So we do the crossover method, or we can see that they are the same. So they're just going to cancel out. So this is our formula, just not written quite correctly. So what matches up? Well, it has to be A. So that is, yeah, with the 2 charges cancelling out. Nice and easy. Right, so on to our next question. So aqueous copper sulfate is electrolyzed using inert electrodes. Which statement about this electrolysis is correct? So we'll just go through them, yeah, one by one this time. So copper ions are attracted to the cathode. Yes, they are. Electrons move from the cathode to the anode. No, they go the other way. The electrolyte ions are oxidized at the cathode. Well, this is not true, as reduction takes place at the cathode. And yes, sulfate ions are reduced to form sulfur dioxide, and this is also not true. So yeah, the sulfate ions never take part in the electrolysis really. So there we go. So it was our first one. It is A. All right, let's move on. So sodium reacts with chlorine to form sodium chloride. The equation is shown. Very nice. During the reaction, sodium atoms blank electrons and chlorine molecules act as blank. Which row competes 1 and 2? Well, we've got all the possible combinations, so let's think about what's going on first before we look at our options. So sodium, when it goes from an element to a compound, is always losing electrons. So it's always losing electrons. And yeah, the chlorine molecules are gaining electrons. So because they're gaining electrons, they are reduced. And if they are reduced, they have to be an oxidizing agent. So the only answer that makes sense is C. Because yeah, it has to be either C or D. And then yeah, this is got the chlorine acting as the oxidizing agent because yeah, it's causing the oxidation to take place. Right, so number 19, which row shows the flame test colors for lithium and sodium? So for this one, we've got a few bonus colors chucked in that aren't at all correct. So from that, this does help us out. So we can just look at lithium first of all. And if we can just remember that lithium is red, we can eliminate A and B straight away because yeah, lilac is actually potassium. So it is either yeah, C or D. And then we just need to remember what sodium is. So yeah, so sodium is yellow. So if you can remember from, you know, maybe before you were born, and there was very old street lights. So street lights used to have sodium in and they had that sort of yellow color. And yeah, that is what was causing the yellow color. It was the sodium. So yeah, so there we go. So our answer here has to be D. Okay, number 20. So a gas is used in welding metals together at high temperatures. The gas is used to provide an atmosphere. So the only one that can do that is a noble gas. So before we even look at the answers, we need to be thinking noble gas. And yeah, our only noble gas is argon. Definitely can't be oxygen or chlorine or fluorine because yeah, they're far too reactive, and yeah, carbon dioxide again isn't great for that. Okay, so which row does not link a general physical property to the type of element? Okay, so we've got metals and non-metals. So I think we need to be thinking about melting and boiling points, conductivity. Yeah, we've got malleability and conductors there. So when looking for does not link them together. So I'm going to just put ticks for which does link them together. So metals are malleable, metals are thermal conductors, non-metals are not electrical conductors, and then non-metals do have a low melting point. So there we go. It has to be C. Alright, iron is extracted from hematite in the blast furnace. Why is limestone added to the furnace? So again, let's start to think about the answer before we look at our answer. So yeah, limestone is used to remove the impurities. So let's see what matches that brief description up. So it decreases the melting point. Nope. It produces calcium oxide, which removes acidic impurities. That sounds about right. And yeah, it produces carbon dioxide to reduce the hematite. No, that's not true. That's what the carbon does. So there we go. So yeah, it has to be C. Right, a piece of iron is coated with a layer of zinc. Which statement explains why zinc prevents iron from rusting, even when the layer of zinc is damaged? So with this here, we need to be remembering, so this is galvanized zinc. We need to be remembering that zinc is above iron in the reactivity series. And yeah, because of this, this undergoes oxidation a lot easier compared to iron. There we go, we can just cut these two. Jumping ahead of myself. So yeah, so iron is less reactive than zinc. So what explanation is going to be correct? So we have zinc atoms lose electrons less easily. Well, that's not true. Use more easily, so that is the true part. So yeah, so more reactive things. So this is true for everything. If something is more reactive, or a metal, metals are more reactive because yeah, they like to lose their electrons more easily. So there we go. That's why our answer is B. All right, sulfuric acid is produced in the contact process. Which substances react together in a reversible reaction in the contact process? Well, what do we have here? Well, it's not this. That is a forward reaction, or not. It's just a one-way reaction. It has to be this one, yeah. So these are both just, yeah, not reversible. So yeah, so our answer is B. So yeah, fortunately this is just something to know. And then I think this is our last question. So why do farmers add limestone to soil? So again, we need to be thinking, what is limestone? So limestone is a base. So yeah, it has to be either these two, because that's talking about pH. So what do bases do? Well, they increase the pH of the soil. So if the soil is slightly too acidic, around 4 or 5, then you add the limestone, and then it brings the pH back up to 7. All right, now let's head over to our next set of questions. Okay, so here we are now with the paper 4. So I've already written in the answers just because you don't want to watch me write every single answer out. It's a bit slow. So we can just make the answers magically appear. So what do we have here? So we've got ethene. So ethene is a member of a family of hydrocarbons. Of course it is. And here is the ethene molecule. State the family of hydrocarbons that ethene is a member of. So we've got the carbon-carbon double bond. So it has to be alkenes. There we go, alkenes. So yeah, ethene is made from larger molecules in petroleum. So anything going from larger to smaller. So ethene is a very small molecule. Yeah, it has to be cracking. So cracking long chain alkane, you get small chain alkane plus the alkene. Polyethene can be made from ethene. Ethene is a polymer. What is meant by a polymer? So yeah, so polymers, we've got the long chain molecule formed from monomers. So yeah, so this is one of the definitions, one of the many definitions that you need to learn. So yeah, definitely learn and remember, yeah, this definition does come up quite a lot. All right, so we've got our table here. It shows some information about polymers. Complete the table. All right, so with this, just highlight this here. So if I just highlight this here, so for all of the additional polymerization reactions, for all the additional polymers, it's like the same basic thing. So you can just imagine ethene without any hydrogens, and then all of the additional polymers are kind of based on that. So all that's getting changed is what's at the end of the bonds. Okay, so if we look at fluoro ethene, we can see that yeah, one of the hydrogens has been swapped by a chlorine. So if we look at the monomer, we can see that that is what has happened. We've just changed one chlorine, or swapped out one hydrogen for one chlorine. Yeah, now if we look at polytetrafluoroethene, so this is got the trade name Teflon, so this is what non-stick pans are coated in. We can see that this time all of the hydrogens have been swapped with fluorines. So let's see how that looks. So there we go, it looks like that. So we can see there is big similarities between these three. It's just that the hydrogens have been changed. Either all of the hydrogens have been changed, or just one of the hydrogens have been changed. Okay, so ethene can be made into ethane. So state the formula of the substance that ethene reacts with to make ethane. Well, we can see we're basically adding hydrogen. Hopefully you can see that. So yeah, our answer is hydrogen. So the hydrogen molecule. So ethane is saturated. Describe what is meant by a saturated hydrocarbon. So again, we've got another definition for you here. So another definition to learn. So what does saturated mean? So only single bonds. Ethene undergoes addition reactions, so it undergoes them with bromine. We've got the equation here. Complete this drawing by showing what is formed. So again, we've got an addition reaction. You're basically just adding bromine to the molecule. So this is what it looks like. So yeah, before we were adding hydrogen, and now we're adding bromine. Okay, question 5. In an experiment, a student adds an alkali to an acid. And we've got the setup there, so our classic titration setup with our burette and then yeah, something underneath. So the student is slowly adding the alkali to the acid. Yep, checks out. We've got the dots there. So describe how the pH of the acid changes as the alkali is added. So this is very similar to our limestone question from the paper 2. So it has to increase. Complete the word equation to show the type of substance that is made in the reaction. So this is one of the classic acid reaction questions. And yeah, we have to have a salt, but we need to remember, definitely remember these equations here, because they come up a lot and then lots of marks are associated with them. Because once you've got the equation, you then need to be like writing an actual equation, and they could ask you to do some moles calculations as well. So yeah, so definitely remembering like an acid plus an alkali is salt and water. Acid plus a base is the same thing, but then also acid and carbonate, giving you the salt, water, carbon dioxide, and yeah, the acid plus a metal, giving you the salt and hydrogen. So definitely remember those 3/4 equations. So yeah, just like I've said, we have now got to write our equation. So we've got sulfuric acid, we've got potassium hydroxide, construct the balanced symbol equation. So we've been given the acid and the alkali, so yeah, we need to form the salt, and yeah, remember that water is getting formed. So we have we've got our acid, we've got the alkali, and then the salt getting formed. So this is the trickiest thing. So the salt getting formed is potassium sulfate and then water. So so with the equations, the first step is to write out all the symbols, and then once you've got all the symbols, then you can do the balancing. And then we need to add the 2 here, because we needed 2 potassiums, so 2 positive potassiums, so both of these are +1, to balance out 2 negative charge of the sulfate ion. So you do need to be remembering the charges of certain ions to make sure we're getting the right formulas here. Or here's a little tip: if you can't quite remember that sulfate is negative by 2, if you remember that hydrogen is always +1, from that you can figure out the charge of the sulfate ion. So this also works with the nitrate ion. So from this we know that nitrate has to be negative by 1. And yeah, hydrochloric acid, again, that's a bit easier, but again, from that we can figure out that chloride is negative by 1. Okay, on to our next question. So state the formula of the ion which is present in solutions of all acids. Well, it has to be the hydrogen ion. So yeah, what is an acidic solution? Well, it is just like a measure of the concentration of the hydrogen ion. So yeah, it has to be present for all acids. All right, on to part B. So we've got ammonium sulfate is made by reacting an acid with an alkali. Calculate the relative formula mass MR of ammonium sulfate. So with this, we've handily got all of the atomic masses there. So we have nitrogen times 2, because there's 2 here, means we've got 2 of everything in the bracket. So we've got hydrogen times 8, sulfur times 1, and then oxygen times 4. So you can use the numbers here, obviously, to put them into the equation, simple equation, and then you'll get 132 once you've added all of those up. So hopefully that's nice and straightforward. Now on to the Haber process. So process you should definitely learn. So an alkali is used to make ammonium sulfate. So ammonia is made by the Haber process. So the Haber process is nitrogen and hydrogen reacting together. And here is that equation. Alright, so describe the Haber process, including the source of nitrogen and hydrogen, and what are the reaction conditions. So we have, so nitrogen comes from the air, and hydrogen comes from natural gas. Then our reaction conditions are 200 atmospheres, 450 degrees, and it is an iron catalyst. So even if you can't remember all 3, or sorry, all four things. It is a 3-mark question, but yeah, this does come up a lot, so I would definitely recommend remembering these conditions here. Yeah, so we've got our reaction conditions here. Okay, so ammonia is reacting with nitric acid to give us a fertilizer, ammonium nitrate. And we've got an equation there, so it's in a 1-to-1 ratio, giving us our ammonium nitrate. Calculate the mass of ammonium nitrate made from 51 kilograms of ammonia. So our first step here is to be calculating, some moles. Let's just look at all of what we've got going on here. So we are calculating the moles of ammonia. We're calculating the moles of ammonia, and because the moles of ammonia is going to equal the same as the moles of ammonium nitrate formed, this is our equation here, but we can kind of arrange it like this. So what's going on here? So this will be, so this side will equal moles of ammonia. This will therefore be the same as the moles of ammonium nitrate, and then from that we can kind of calculate the mass, which is what we have done over here. So here we go. So we have, let's do some highlighting. So here is our mass, here is the MR of ammonia, and then the MR for the ammonium nitrate. And then that will then give us our answer of 240 kilograms. So because our final answer is in kilograms, this is in kilograms, we don't need to worry about converting between grams, and then back to kilograms. Okay, so on to our next question. So number 8, look at all of these lovely numbers. Complete table 8.1. So proton numbers. So using the periodic table, that's where we can get our answers. So each element has its own proton number, and for argon that is 18. And then our electronic configurations. So magnesium has this electronic configuration. So remember, it goes here 2, 8, 8, 2. So that's all you need to know. But once you've kind of filled up as far as you've gone, then you can stop. So a nice easy 2 marks there. Okay, what is meant by an isotope? So again, this is another definition to remember. So we need to definitely learn what an isotope is. So we've got the same proton number, so each element has its own unique proton number. But we have a different number of neutrons. You could also say a different nucleon number if you want, that's also fine. But I just like to put it as a different number of neutrons. Alright, so why do 2 isotopes of chlorine have the same chemical properties? So chemical properties are never dictated by the number of neutrons, they're always dictated by the electronic configuration. So what is our answer? So they've got the same electronic structure. So that's really important. Chemical properties is always linking to electrons. Okay, argon is a noble gas. Explain why it is very unreactive. Well, it's because it has a full outer shell. So this is why all of the elements are reacting, apart from group 8. They're trying to get a full outer shell. If you've got a full outer shell, you don't need to do any reacting. Okay, sodium is a metal. Describe the bonding of metal. You may draw a diagram to help your answer. Well, I did not draw a diagram. I wrote down that it's a lattice of positive ions surrounded by a sea of delocalized electrons. So what would that look like in diagram form? So we've got our regular arrangement of our positive ions. So we can put these as little positives, and then they're surrounded by electrons. So how would that look like? It would just look like little dots everywhere. So there we go, nothing too fancy about this diagram. Lovely stuff. Alright, magnesium chloride contains the ions Mg2+ and Cl-. Determine the formula for magnesium chloride. Well, we've already done something very similar in the paper 2. So it is the valency swapping over method. So so Mg's got the 2, chlorine's got the 1. They get swapped over, and that's how we end up with our formula here. Nice and easy. Okay, fluorine reacts with sodium chloride. Construct the balanced symbol equation for this reaction. So this is the displacement of halogens. At the top, they are the most reactive. So fluorine's at the top, is the most reactive. So it's a displacement reaction. The fluorine is kicking out the chlorine, as we can see here. So yeah, so the fluorine is kicking out the chlorine to make sodium fluoride, and then the elemental chlorine is getting formed. But because we've got these little 2's here, then we need to add the big 2's over here. Happy days. Okay, let's look at our next question. So a student investigates indigestion tablets. These tablets neutralize acids, which is what you'd hope them to do. The student measures out 50 centimeters cubed of dilute hydrochloric acid into a beaker. He adds the tablet, and then this is what the lovely experiment looks like. Very nice. The student measures the time the tablet takes to react completely. He repeats the experiment, but makes one change each time. So let's have a look at what's going on. So we've got some different volumes, using some different acids, and we've got some different temperatures, and then here are our results. So lots of different things going on. So the volume of acid does not affect the rate of reaction. So which 2 experiments show this? Well, it is experiment 2 and 3. So here we have different volumes. Everything else is the same, but we can see that the time taken for the tablet to dissolve is the same. So there we go. And this is true, so volume does not, if the concentration is the same, volume does not affect the rate of reaction. Some people think it does. Don't know that be you. Okay, so increasing the temperature of the acid affects the rate of reaction. Increasing the concentration of the acid also affects the rate of reaction. For each factor, temperature and concentration, describe how the rate of reaction changes and why the rate of reaction changes using the ideas about particles. Okay, so this does come up a lot, and the answers are, it has to be very, very specific. So let's see what we've got written down first of all. So we have, so how the rate of reaction, so it increases with temperature, that's the easy mark. The explanation is a little bit trickier. So so it's because particles have more kinetic energy, and then the second thing is that they have an energy greater than the activation energy. So this is really important with temperature. Not only do they have more energy, it's that that energy is greater than the activation energy, so that's how they can react. And with our concentration, so the first mark's easy, increases with concentration, and then the second thing is more particles per unit volume. So this is the really important part, per unit volume. If you say more particles, you're not going to get the mark. It's more particles per unit volume. So again, this is why the volume thing doesn't affect it. If you had a bigger volume, you do have more particles, but the rate of reaction is the same. What you need is more particles per unit volume. So more particles in the same space. Okay, we're on to C. So experiment 1, the student uses dilute hydrochloric acid with a concentration of 0.1. Calculate the concentration of the acid. So nice, simple calculation, I hope. So so concentration is just the number of moles times its atomic mass. There we are. On to D. So the reaction between the indigestion tablet and the acid is an exothermic reaction. Use ideas about bond breaking and bond making to explain this. So if you can't quite remember about bond making and bond breaking, this might be a bit tricky. But so we have the first part of the answer here. So bond breaking is always endothermic. So to break bonds, that always requires energy. Doesn't matter what the bond is. And then bond forming is always exothermic. So as soon as atoms come back together again and form a new bond, that's always exothermic. And then comparing how much energy is needed compared to how much energy is released determines if the reaction is exothermic or endothermic. So with our exothermic reaction, more energy is given out than taken in. So more energy is formed, given out when the atoms form, compared to the energy needed to break the bonds in the first place. We're now on to our final paper, so paper 6. So with paper 6 is a lot of reading. Make sure you do the reading so you can understand the experiment. And then from that, the questions, most of them are quite straightforward. Okay, so I've got a lot of reading to crack on with. So a student is doing an experiment to find this value of X. So how many waters basically become part of the copper sulfate structure when it is hydrated. So what have they done? So they have heated the blue copper sulfate crystals to remove the water. So yeah, so that lovely blue colour is coming from the water being part of the structure. So yeah, this is hydrated copper sulfate. Now we're getting anhydrous copper sulfate and the water. So yeah, so the dry white copper sulfate powder is formed, and the water vapor is released. So what are they doing? So they are finding the mass of the empty evaporating basin, recording it in a table, adding the blue copper sulfate crystals to the basin. They're then going to find the total mass of the evaporating basin and the copper sulfate crystals, recording this in the table. They are then going to place the evaporating basin on top of a tripod and gauze. They're going to heat it until we're getting the white copper sulfate. They're going to leave it to cool, and then they're going to find the total mass of the copper sulfate powder at the end. Okay, so before we look at the results, we're being asked to draw a diagram. So we are just doing a simple heating up. So this is the tripod, Bunsen burner, the gauze, and it looks like this. And it also wants some labels. So labeling the apparatus and the copper sulfate crystals. So most of the marks are actually coming from the labeling. So so make sure that we've got everything drawn properly. So our Bunsen burner, tripod, gauze, heat-proof mat is needed. Evaporating basin, and then we've got our copper sulfate crystals. Always add more labels. So you're not going to get marks for all of the labels, but sometimes you might get a label for gauze. Sometimes you might get the mark for tripod. You don't know. So always add labels for absolutely everything, because you don't know exactly which thing is going to be counted for. Okay, so here we go. So copper sulfate crystals are blue, copper sulfate powder is white. Suggest how the student knows when all of the water has been removed. Well, we've got a colour change, so it's probably going to do with that. So so once it's all white and there's no more blue left, then hopefully the reaction should have finished. Okay, so this is some pretty classic stuff with a paper 6. Is you've got some information that you need to record in the results table. So nice and straightforward. We have our numbers there, but what we do need to do is record to 2 decimal places. So don't just hastily jump in and record this. Yes, it's asked us to 2 decimal places. Another common one would be like time, and time when you measure it on a stopwatch is in like minutes and seconds, but the results table is only in seconds. So making sure you are fully reading the question. So so we've got our 2 numbers there. And then paper 6s, they kind of give you the calculations. You just need to be putting in the right numbers to kind of get the answers. So that's what we've got here. So calculate the mass of water loss by by the crystals. So there we go. We've got our answer there. Again, we've got our equation. Calculate the amount of water in the copper sulfate crystals. So so this is in moles. So 0.113 moles. Another calculation to do. So again, we're just putting in some numbers, and what are we getting? 3.849. So this is the mass of the dry copper sulfate powder. Calculate the amount of dry copper sulfate powder. Again, we've got the equation. So here we go. So this is the number of moles of the dry copper sulfate powder. Now, using our answers, we can figure out what X is. So amount of water divided by the dry copper sulfate powder. Give your answer to one significant figure. So here we go, it is 5. So it has to be a whole number, because you can't have 0.5 point whatever of a molecule of water. So this has to be a whole number. Okay, suggest what the student can do to have more confidence in the value of X. This question is a little bit trickier, but so kind of repeat the final stages of the experiment, or repeat all the experiment and get an average. The student did it and they found that they had a larger value than expected. Why could it be larger than expected? So what could have happened? Not all of the water would have evaporated. So if not all of the water was evaporated, then you're going to get a large value. Suggest how the student can change the white copper sulfate back to blue copper sulfate? Well, if you remove the water and it made it white, logic would suggest that if you added water, it's going to go back to blue. So there we go, 15 questions, and overall I'd say those are pretty straightforward. You're just kind of following through the method, but making sure you read in detail what you need to do as you go along. Okay, on to the dreaded ion identification. So people are really not a fan of these questions, but you do now have all of the tests. The tests are now given to you in the paper 6 at the back. So make sure you use that, because that is a huge amount of help, and it's really going to help you when answering these questions. So what is going on? So a student does some tests on solution R, S and T, and then we've got our results here. So lots of results. Let's not read all of that, but we can enjoy it for what it is. So with these tests, you need to be thinking about, like actively thinking about, what is the test trying to show us, and then what are the results showing us, because the results can either prove something or disprove something. But even like the absence of a positive result is still telling you something about about your solution. And then always remembering, you've got a positive ion and a negative ion, and you've got different tests for each. Okay, so let's have a look at the question. So use the results in table 4.1 to describe two tests you could use to identify a sample of solution T, including the observation in your answer. So, and then explain why each test can be used to identify T and not R or S. So what do we have? So we have our answers here. So a flame test. So our flame test is giving us an observation of yellow. The others are red. So let's have a look here. There we go. Ooh. So our flame test, so these are the same, this is different, so we can use that to figure out we've got T. And our other one, aqueous sodium hydroxide, so this is testing for cations. So let's see what is going on over here. So so a few drops of aqueous sodium hydroxide, colourless, and then these are forming white. So again, because we're getting this unique result, this is how we can identify T. Okay, use the results table to describe one test you could use to identify a sample of solution S. So nitric acid, and that's giving us a cream precipitate. So let's see what's going on. So the nitric acid. So we can see same, and then our different results. So whenever you're getting a different result, you can use that to identify that one thing it's going to single it out. Oh, there we go, we're all done. So thank you for watching all the way to the end. I hope you found this useful. So please do like and subscribe and tell all of your chemistry friends about these videos. It will really help the channel. And if you are in need of some extra chemistry help, then please do check out my website. The link is in the description, and there you can find out details about how to have some chemistry tutoring from me. Alright, so I will catch you in the next one, and good luck in those exams. Ciao!